Hello AP Physics 1 students. This is going to take the place of the lesson that we would have had we not had that extended drill during class last time. So please make sure you have your notebook in front of you, where it is you usually take your handwritten notes, as well as your Newton's Laws problems packet. So if you have both those in front of you, you're good to go. If not, please pause the video, get them in front of you, so you're ready to take notes and do some problems. So first I want us to look back at problem number 2. This is the problem with the bucket. We're looking at parts A and C. In part A, you'll remember that the bucket was at rest on the ground, and the normal force was supporting the weight with a force equal to the weight of 27 newtons. Then in part C, the bucket was in motion, rising at a constant speed, where now the tension was supporting the weight with a force equal to the weight of 27 newtons. And so we have this interesting situation where in both cases the weight is supported by something, and so we want to look at the similarities and differences. So similarities, well, if the weight is supported by another force, the weight is cancelled out by another force, that means the net force equals 0. That means that the acceleration is also equal to 0. And yet, the main difference is that in letter A, the bucket was at rest, and in part C, the bucket was in motion. And so we see that just knowledge that the net force is 0 or the acceleration is 0 of the object does not necessarily tell you whether the object is in motion or not. But both situations are known as equilibrium. So here in our notes, we're going to make a chart of the situation known as equilibrium versus not equilibrium. There's no good physics term for not equilibrium. It's not disequilibrium or unequilibrium. We're just going to call it not equilibrium. And so on the equilibrium side, the real definition is this, that sigma f equals 0. Here we remind ourselves that sigma f is the vector sum. So you put all the forces together, and if they cancel each other out, we call this equilibrium. What does it mean for not equilibrium? Well, it just means that sigma f is not 0. Here you add the forces as vectors, and something is left over. What's the result of this? Well, back on the equilibrium side, if sigma f equals 0, that means the acceleration equals 0 from sigma f equals ma. And so you might guess that on not equilibrium side, what does this mean? It just means the acceleration is not 0. Now I know some students like the words better than symbols, so on the not equilibrium side, we'll say the object is accelerating. That's what it means to have the acceleration not 0. It is accelerating. And back on the equilibrium side, that means it is not accelerating. So back on the not equilibrium side, well, again, what does it mean to be accelerating? Well, we know there's 3 different ways the object could be accelerating. It's either speeding up, slowing down, or changing direction. And of course, it could be doing a combination of these things. But as long as it's either speeding up, slowing down, or changing direction, it is accelerating. It is not in equilibrium. So what does it mean for equilibrium? What is it not doing? Well, it can't be doing any one of those things. It can't be speeding up, slowing down, or changing direction. And you can just show it as I have here with the arrow. You don't have to write them again if you don't want to. Back to the not equilibrium side, so what is happening? Well, it means that it must be changing velocity. Anytime the object's velocity is changing, it's not in equilibrium. So back to equilibrium, what is happening there? Well, as we showed before, just because it's in equilibrium, just because the acceleration is 0, does that mean it's not moving? No, of course not. The bucket was in motion. So what's happening? It may be moving, but just with a constant velocity. The other question is, could it be at rest? Well, of course it could be at rest. That was what the bucket was doing originally. So it's either moving with a constant velocity or it could possibly be at rest. Either one of those is the situation equilibrium. And again, if all you know is that the net force is 0 or the acceleration is 0, you don't know if it's either moving with a constant velocity or if it's at rest. All you know is nothing is changing about its velocity. Let's now go back to our problem set. We're going to pick back up with problem number 5. So let's turn to problem number 5. Looks like this. Read it. Start with a free body diagram, information off to the side, solve it in full. Even though it's a very simple problem, I want you to solve it in full with an entire free body diagram, show all your work. Pause the video and go ahead and do that. Okay, just in case you missed any steps, I'm going to go through it step by step. So normally, before we even do the free body diagram, we put some information off to the side. For example, we put the velocity, and we see that on this frictionless surface it's being pulled to the right, so of course it's going to move to the right. We put velocity off to the side because remember, it is not a force. It's measured in meters per second, not newtons. We also put acceleration off to the side. So if it's being pulled to the right and there's nothing opposing that pull, it will accelerate to the right. In this case, as long as it starts from rest, it will speed up to the right. Acceleration is also not put on the free body diagram because it is not a force. It is measured in meters per second squared. The third vector we put off to the side here is sigma f. And remember, from sigma f equals ma, the direction of acceleration is always the same as the direction of the net force. And so in this case, the acceleration is to the right, the net force, or sigma f, is to the right as well. Now remember, sigma f, even though it's measured in newtons, is not a single force. It's the result of putting together all the forces that you'll see eventually on the free body diagram. This means that sigma f will never appear on the free body diagram. We always put it off to the side somewhere. The next step is to assign a positive direction. It should be pretty clear, since everything's pointing to the right, that we're going to call to the right positive. So I like to label it over here by one of the other vectors, maybe here by the velocity vector. Alright, now it's time to do the actual free body diagram, and just so we fall into routine, we always want to start with a force that's pretty much always going to be there, and that's the force of gravity, also known as weight, and it always points straight down. So there it is. There's mg. I like to symbolize the mg, but if you want to call it f sub g, or f grav, or w, it's all good. I'm going to keep writing it mg. And if you know the mass, it's a good idea to calculate it right away. There's 3 sig figs in the mass, so there's 3 sig figs in the weight, so it's 118 newtons. What else is acting on it? Well, we have the normal force, right? It's pressing against the surface responds, and since nothing's happening vertically, it's just supporting the weight. And so it's also equal to 118 newtons. The other force is, of course, shown in the free body diagram already there in the picture. That's the 49 newtons to the right. It's just labeled capital F because we don't really know where this force is coming from. We don't really care where the force is coming from. It's just 49 newtons to the right. The next step is, of course, to write sigma F equals ma and rearrange as necessary. Here we're finding the acceleration, so it's sigma F over m. The normal force and weight will cancel out, leaving only the 49 newtons to the right divided by the 12 kilograms. We have a magnitude of the acceleration of 4.08 meters per second squared. A very standard, very easy problem, and really, you probably didn't have to show all this work, but it was good practice to draw the free body diagram, identify all the other vectors to the side, establish a positive direction, and get in the habit of doing this. Alright, so let's go ahead to problem 6, where it gets more interesting. So here we have two objects, 7 kilograms and 5 kilograms, attached by a string in the middle, and also moving along a horizontal frictionless surface and pulled to the right with 49 newtons. I want you to pause the video here, start from scratch, put information off to the side, do separate free body diagrams, and then come back and we'll solve it together from there. Okay, so since these two are going to move together, really you can just put single velocity, acceleration, and net force vectors. And so it's being pulled to the right, it's a frictionless surface, nothing's holding it back, it's going to move to the right, it's going to accelerate to the right, and the system will have a net force to the right, and so to the right is a good positive direction. And again, I'm putting these way off to the sides, they're not even close to the free body diagram. If you didn't do that, maybe you want to do that, make sure they're very far away. The problem set itself maybe didn't really have enough room to draw the free body diagram right there on the diagram, but there's plenty of space underneath the two pictures to draw your separate free body diagrams, but if you could squeeze it in, that's fine as well. Alright, so focusing on the 7 kilogram object, we always want to start with what force is always there, and that's the force of gravity, also known as weight, pointing straight down. And you go ahead and calculate 68.6 newtons. And of course, it's supported by the surface, so there's normal force up, supporting the weight of 68.6 newtons. Did you have anything else in your free body diagram? Well, hopefully you did, because there is a string touching the 7 kilogram object. If there's a string, there will have to be a tension, which of course is a big clue about that with that T right there on the picture, and the fact that the problem asks you to find the magnitude of the tension. Which way does the tension point? Well, we talked about this in class, that when you attach a string to an object, you're going to pull with that string. Imagine attaching a string to an object and trying to push with the string. The string's just going to go all wobbly. It's not going to go anywhere. It's not going to work. And so you're only going to be able to pull. So tensions only pull. So if the string is to the right, the tension is to the right. And notice I put the arrow for the vector of tension right here on the string. I strongly suggest you do the same. And if you need to, pause the video and redo that. That's a good idea. The reason why I ask students to do that is I found in the past that if students instead put a separate vector over here for the tension, some students see that tension force and then also see the string touching it and think that there are two forces to the right in this case, and of course that's not true. The tension is the force from the string. Alright, going over to the 5 kilogram object, we start with our usual, that there's going to be weight straight down, 49 newtons. Normal force is up 49 newtons, just supporting the weight. There's already that external force of 49 newtons to the right, and since the string is touching the 5 kilogram object, there's tension in this string as well. It's already sort of labeled by T from the picture, but maybe it's a good idea to label this as capital T as well. And remember, we talked about this fact that if it's the same string, it's the same magnitude of tension. If you go back to your notes on tension, we also mentioned that tension points both ways, and that's really what we're showing here, is that within this one string, the tension force is pointing both ways. Now, just to be very, very clear though, those two forces are acting on different objects. So some students get a little confused and see these two tensions, pointing against each other and say, oh, they must cancel. Well, that's not true. This tension over here is acting on only the 7 kilogram object. This tension over here is acting on only the 5 kilogram object. And if the forces act on different objects, then they can't cancel each other. This is why we really draw a free body diagram isolating the two objects so we can see the forces acting on each individual object. Okay, so what happens next? Well, we're going to write sigma F equals ma for each individual object. So we start with the 7 kilogram object. We write sigma F equals ma. And we see that the weight and the normal force are going to cancel, leaving only the tension as the net force. We called right positive, so we'll write this as positive T. The mass is 7 kilograms, so we can write it as positive T equals 7 kilograms times A, the unknown acceleration. Here we have an equation with two unknowns. There's nothing more we can do with this, and so now we just go over to the 5 kilogram. We'll do the same thing. In fact, I'd like you to pause the video, write sigma F equals ma, and then take the next step of combining the forces with their proper signs on the left side to build up sigma F. This is what it should look like. We've got sigma F equals ma, and then the very next thing is to look at all the forces acting, looking at our free body diagram, use our proper positive direction, and list them as necessary. So we have the 49 newtons to the right, and right is positive, we list it as positive 49. The tension is pointing to the left, so we list it as negative T. This way we take care of the direction with the sign. The mass here is 5 kilograms, and so it's 49 minus T equals 5 kilograms times the acceleration. Now at this point, you may be wondering, what about the different accelerations? Which of these two objects, the 7 or the 5, will accelerate faster? So take a second and think about that, pause the video, then come back after you have an idea. Okay, so I know from experience that some students will say, well, the 5 kilogram has less mass, so clearly it will accelerate faster. And that is absolutely true. By sigma F equals ma, if the net force is the same, a smaller mass means a larger acceleration. But that's if the net force is the same. Let's just imagine that if we take these two objects with a string attached and pull to the right along this frictionless surface, if the 5 kilogram were to accelerate faster than the 7, visualize it, what would actually happen? In your mind, you should be able to see the 5 kilogram would race ahead of the 7 kilograms and the string in the middle would break. And since the problem says nothing about the string in the middle breaking, we're going to have to assume that the system actually stays together. And so these objects will move together and accelerate together. We'll come back to this idea of why the 5 kilogram does not have a smaller acceleration in terms of the net force when we're done solving the problem. Okay, so now if we look at our two equations, we've got two equations and two unknowns. This is a solvable system. We can go ahead and do a substitution. So let's say here that T equals 7a, and this goes right in here where this says T. And here I've eliminated the units just to make it look more like a math equation from algebra. So we have 49 minus 7a, where 7a is the tension, right from here. Here's the 7a, there's the 7a, equals 5a, again removing the units. And so now we just solve this for a, moving the 7a to the other side, so it's 49 equals 12a. Solve from there, a equals 49 over 12. Now I put the units back in to remind ourselves what these actually mean. So it's 49 newtons divided by 12 kilograms equals an acceleration of 4.08 meters per second squared. We can put this acceleration back into the tension equation, and you should be getting 28.6 newtons. Now at this point, you may have noticed something a little bit interesting. So let's go back to problem 5 and see it right next to problem 6. So here's problem 5 at the top, and here's problem 6 on the bottom. And you should notice that we got the exact same acceleration. So why did that happen? Take a look at it and really think it through. Now some of you immediately might say, well, in problem 5 there's 12 kilograms, and problem 6 was a total of 12 kilograms, and that's good, but there's got to be more than that. Why did we get the exact same acceleration? So hopefully you noticed that in problem 5 there was 49 newtons acting on 12 kilograms, and in problem 6 there was 49 newtons to the right, over here, acting on a total of 12 kilograms, and so we got really the same exact acceleration, the same equation. So that should make sense, right? If we go back to problem 5, it's 12 kilograms, and we take those 12 kilograms, break it into two pieces of 7 and 5, put it on the same frictionless surface, draw a string between them, and pull to the right with 49 newtons, we should expect that we should get the exact same acceleration. Why would you not? So that's a very interesting result. Okay, so let's go on to problem 7. Problem 7 looks like this, where now we take the 7 and the 5 kilogram objects, the string is attached between them, and now the string passes over a pulley. This circle here represents a pulley, which is really just a way for the string to be redirected into a new direction, in this case from horizontal to vertical. And we'll assume the pulley is ideal, that its mass doesn't matter, and that's a frictionless pulley, which, later on in the year we'll talk about what really happens when it does have mass and when there's friction involved. Although I will tell you that years ago I saw massless, frictionless pulleys advertised in the science supply catalog, so I was very excited. I bought a big box of them. The box came. I opened it up, and it was empty. Yes, the jokes are still that bad right over YouTube.